we were discussing the guiding properties of the basic waveguide, that is a dielectric planar slab, in terms of the TE-TM mode, the field distribution across the waveguide, the eigenvalue equation and related parameters. And now we will discuss some more guided mode properties which are very important and relevant, particularly in terms of device applications like power associated, orthogonality of modes, real eigenvalue. So, from that point of view, we organize this discussion under the following points: some key properties of the guided modes, power carried by the modes, T and Tm modes, and we will see the eigenvalues of the wave equation are real, and we will also as a consequence see that the guided modes are orthogonal to each other. And then another very relevant discussion is the radiation modes and corresponding fields. So, we will see that it forms a continuum of radiation modes for certain condition of the propagation constant. So, power flow associated with a mode. Know that the power associated with a mode can be determined from the calculation of Poynting vectors. Time average of S is equal to half the real part of this E cross H star, where H star is the complex conjugate of the magnetic field vector. First, we will consider the case of a planar dielectric slab waveguide and the TM modes, and we will see that this understanding this calculation is also valid for the other modes and approximately valid for almost all such waveguides. So, for TE modes, we represent the electric field in this way: U y equal to the amplitude E 0 y as a function of x, which varies across the waveguide dimension s x, and this phase factor e to the power of I omega t minus beta z. Now, H x and E y, they are connected, we have seen through this expression, which is a consequence of the Maxwell's equation, and writing explicitly the electric field we can write in this form. Now, E z, H z is also connected to E y through this equation, and these two equations will be used to calculate the Poynting vector, because for a TE mode you have E y, H x and H z. We will translate H x and H z in terms of E y using this equation, and then we can evaluate. So, using these relations, these connection relations, we can rewrite. So, for the S component of the Poynting vector, that is the Poynting vector which is to determine any energy flow along the x direction, we need to write this equation in this form: half real part of E cross H star and the x component of that. So, E cross H star can be written in this form: E y H z star minus E z H y star, but E z for a TE mode E z equal to 0. So, this second quantity does not appear, only this E y H z star we will have to calculate, and then this S of x becomes half of real part of this quantity, because H z star we can translate into E y using this equation. H z will be expressed using this equation. So, so this equation, but this is equal to 0, because if I substitute for U y for the symmetric TE mode, it is a cosine kappa x, and the derivative of this will give you sin kappa x. The product of this and time averaged over this will become always 0. Time average of sin x and cosine x over a period is 0, and vice versa. If you take the antisymmetric mode, then sine function after the derivative, it will become a cosine, and this will lead to the same consequence, that is this quantity will become equal to 0. That means, there is no power flow along the x direction. There is no power flow along the x direction of the waveguide. Now, if we calculate the y component of the of the Poynting vector, then in the same way we can represent that half of real part of E cross H star, y component of that. This will lead to half of real part of E z H x minus E x H z star, and that is equal to 0 because E z and E x both are 0. So, E z and E x both are appearing here. So, that is why this quantity equal to 0. It tells you that there is no power flow along the y direction as well. Now, let us check the power flow in the z direction, and for that we calculate the time average of the z component of the Poynting vector. In the same way we express this quantity in terms of E and z, E and H star, and when you expand this, take the z component of E cross H, you can write this E x H y star minus E y H x star, and because again H y is equal to 0 for TE mode. So, we end up with this quantity, and then we can write this equation as if we translate H x using that relation, then you can write that this equal to beta by twice mu naught omega E y mod square. So, this is the power flow along this z. This also tells you that along the direction of propagation, that is along z direction, power only flows through the waveguide. And as a matter of fact, if we do this calculation, and we will see that this relation is approximately valid for all waveguides under the weakly guiding approximation. Okay, now, to evaluate this power in terms of the known quantities, we write this expression, and we will have to integrate it from minus infinity to plus infinity, and this E y square will be replaced by this expression which is valid for the core, that is when mod x is less than d by 2. Remember the waveguide structure, and this is the evanescently decaying part of the field which is there outside the core region, that is in the cladding region for x mod of x greater than d by 2. So, if we substitute the value of E mod square, we can write in this form a square cosine square kappa x plus c square e to the power of minus twice gamma x dx, if we consider the symmetric mode. And then if you do this algebra, you can write this cosine square kappa x as 1 plus cosine twice kappa x dx, and this remains as it is, and it follows that we can, after if we do this integration, this quantity, then we can write that p equal to this a square d by 2 sine of 2 k d by 2 by twice k plus c square e to the power of this twice gamma d by 2. I retain this d by 2 because we can use this k d by 2 this factor for utilizing this eigenvalue equation. So, if you take 2 outside, then it reduces to this form. Now, we will use the continuity of the field at d by 2. So, E y at d by 2 is equal to this, and at for the cladding part, that is outside the core, at the interface actually we are matching this field. So, we can write these two are equal. So, from here we can write c square by a square times this will be equal to. So, that we have an intention to replace this c square by a square in terms of cosine kappa d by 2, and after doing that you can rewrite this equation in this form. So, beta by twice mu naught omega a square d plus twice by gamma, this is the form. Now, if you take twice kappa d, twice sine kappa d by 2, cosine kappa d by 2 and gamma k outside, then we can write gamma minus k tan kappa d by 2, and this quantity, this expression is well known because it is the eigenvalue equation for the symmetric T mode gamma equal to kappa tan kappa d by 2. So, this quantity becomes 0. Therefore, we end up with only this quantity, and we can write the power flow, the content of the power per unit length of the waveguide by this expression beta by twice mu naught omega a square d plus 2 by gamma, and gamma is it also represents the depth of penetration of the field in the 1 upon gamma in the cladding region. So, this expression gives you the total power flowing with the along the waveguide per unit length of the waveguide. Now, for a planar dielectric slab, we calculated the power carried by a symmetric TE mode, which is equal to this, and if you follow the same calculation, then we can also calculate, we can also determine the power carried by the antisymmetric mode, because in that case, in place of the sine function, we can use the in place of cosine function, we can use the sine function to represent the antisymmetric mode. The derivative of that will be cosine, and again it will be only the z component of power, and this will turn out to be the same as the symmetric TE mode, the same value we will have. Now, this power carried by, so symmetric and antisymmetric modes for both TE and for the TE mode of the waveguide will result the same power flow expression, and for the power carried by TM modes, both for symmetric and antisymmetric modes, we can in the same way we can show, following the same calculation, we can show that this also can be represented by this expression, where additionally you have n 1 n 2 square, n 1 square, n 2 square, and this is usual because this appears n 1 and n 2 square appears as the continuity of the magnetic field across the interface. Okay, now we will look at another important aspect of the waveguide modes, which is the orthogonality of modes, and this is very interesting to know that all the modes which are supported by the waveguide will be orthogonal to each other. For that, we write the wave equation for the electric field for this particular case, that is for the TE mode, and the electric field of that is u I. So, we can write this expression k 0, this is n square of x to represent both core and cladding, and so if we consider the mth mode, and we can write the mode by writing this psi m as the mode designation, then del square psi m dx square and k 0 n square psi m will be equal to lambda m. This lambda m, which is to represent this beta square, is the eigenvalue of this eigenvalue equation. So, this wave equation and eigenvalue equation will result the eigenvalue lambda m, and so that is what that beta square equal to lambda m denote the eigenvalue of the operator this. So, you can treat this quantity as an operator which is operating on psi m, will give psi m back with the eigenvalue lambda m. Now, for psi m, this is the equation, and if we take the complex conjugate of the above equation for a different mode, that is del square psi k del x square and then k 0 n square of psi k equal to, then we should write lambda k star psi k. And now, if we multiply these two equations, assuming that psi m and psi k they are different, then respectively, and then if we subtract, we can write this equation in this form. Multiply this equation by psi k star and this equation by psi m. So, we get this equation. It is very interesting to note that from here this quantity, the left hand side is 0. Why? Because if you look at the left hand side, this quantity can be expressed as d dx of psi k star del psi m del x minus psi m del psi k del x, and this involves psi k and psi m, which, so you can write in this form, and d dx of this, which if you integrate over the whole space both sides, then you can write this equation as minus infinity to plus infinity integration of this will give you this quantity, which is equal to psi k dx and dx. So, this will be the result of the integration psi k star, and but this is equal to 0 because the psi m and psi k for guided modes will vanish as x tends to infinity, plus infinity and minus infinity. The fields will become 0 far away from the waveguide across the along the side length. So, we see that this quantity lambda m minus lambda k star and integration from minus infinity to plus infinity psi k star psi m dx equal to 0 is a very well known form of this integral. So, this tells you that there are two possibilities. One is that k and m they are equal, that is the two modes k equal to m they are the same modes, that means then this integration, if this is equal to 0, so then this is non-zero, this is non-zero. So, psi m square dx will be always positive, because for one mode k equal to m, this becomes this m psi m star psi m will be equal to mod psi m square, which is the probability of this function. So, it is always positive and finite. So, it cannot be 0. In that case, the lambda m minus lambda k star, that is the eigenvalues, difference of the eigenvalues are 0, which immediately tells you that lambda m is equal to lambda k star. That means, for the modes, the eigenvalues, all eigenvalues, that is the beta square, which was represented by lambda m and lambda k, are real. This is a very important consequence of this understanding. So, we have this expression, and if we look at the second possibility, that is for k not equal to m, in that case lambda m minus lambda k not equal to 0, it means that this must be equal to 0, this integrand will be equal to 0, and this integration 0 means this is the orthogonality condition, that the product of these two, the inner product of these two wave functions will be always equal to 0. So, these are two very useful outcome of this mode properties, guided modes of the waveguides, and that is true for all waveguides. Now, look at this orthogonality condition. When m equal to 0, you have this mode, which is the fundamental mode for a symmetric planar dielectric structure, and when m equal to 1, that is the first order mode, then you have an antisymmetric distribution of the field. So, that has this shape. Now, if you take the product of these two wave functions, that is psi 0 and psi 1, if you take the product of these two wave functions psi 0 and psi 1, so this product, that is I look at the product only at the left hand side, that is psi 0 and psi 1, and I integrate. So, this quantity multiplied by this quantity, the area under this will be same as this quantity multiplied by this, because across this line the left hand side area and the right hand side areas are same. So, this integral and this integral, both of them are equal, but they are having opposite sign, because the product psi 0 and minus psi 1, here the product is psi 0 and plus psi 1. So, they will cancel each other, and the result is that this product summed over the total psi 1 psi 2 over the entire waveguide will be equal to 0. That is what is the orthogonality, and this is true for every mode to every other mode. For example, if we take m equal to 1, that is the first antisymmetric mode, and the second symmetric mode, that is m equal to 2, which has a field distribution like this, and again if we compute the overlap. So, this psi 1 is here and this part. So, this part multiplied entirely psi 2 and psi 1 will give you the left hand side, and similarly psi 2, psi 1 plus and psi 2 on the right hand side, they will give you the same value, and with a minus sign for this part and this part, and for plus sign for this part and this part, which will be put to, when if you put equal to, will be equal to 0. So, that means that for every mode to every other mode, we can do this same calculation and see that modes are orthogonal. This is a very interesting property and seen in the quantum mechanics also. Now, radiation mode, for the modes, guided modes, the condition is this, that this beta by k 0 square, that is what we call the ineffective square, will be always lying between n 1 square and n 2 square. This should be n 2, this is by mistake, this should be n 2. So, will be between n 1 and n 2 square. The class of modes for which beta falls in this regime, that is beta square by k 0 square, this ineffective value, ineffective will be less than n 2 square. In that case, the modes will be called the radiation mode. And why it is so? We can see that let us recall any of the wave equations, for example, say TE mode, then we can write down this equation which is well known again, and in the region that is mod x greater than d by 2, the wave equation, that is in the cladding region, the wave equation can be written in this form, because this n square of x will be a constant value n 2 square, and this equation to be satisfied, we can write this expression. Earlier we called this is the mode parameter or the transverse component of the propagation vector. Here we write this equation as delta square, and so that this delta square is equal to k 0 square n 2 square minus beta square. And this equation is also well known in physics, and we can write the solution as E y is equal to e to the power of plus minus I delta x. So, that is what. So, now for beta satisfying the condition beta square by k 0 square less than this, we have this quantity which is now positive, because of the difference of this quantity is now positive. Therefore, the solution to the wave equation in this region, that is in the cladding region, can be expressed in terms of this. That is what I just told, that the solution of this equation will be, because delta is now positive. So, we can write this equation U y is equal to approximately equal to this plus minus e to the power of I. The solution is in this form. Okay. So, U y is e to the power of plus minus I delta x. That means evidently these modes are oscillatory. For a mode to be guided, the condition is that it should be an oscillatory function in the core, but an exponentially decaying function, evanescently decaying function in the cladding. But it is seen from this condition that if we assume that n effective is less than n 2, then the modes are, the fields are oscillatory even in the cladding region, and which is different from the guided modes which are exponentially decaying. And also we can see that delta can assume any continuous value, because there is no restriction on delta now. So, the value which condition above, the radiation modes are continuous, and which is different from the discrete guided modes of the waveguide. So, we have seen that for this condition you have a set of continuum modes which are the radiation mode, but actually from the ray theory you can see that these waves, the rays corresponding to these waves do not satisfy the critical angle condition, and that is why they are refracted out from the interface, and it forms a continuum of radiation modes. So, in this discussion we summarize that we have discussed the power carried by the guided modes. We calculated for the TE modes of a slab waveguide for symmetric field distribution and also for antisymmetric field distribution. We have seen that if we carry out the similar calculation for TM modes, we can also determine the power flow with the waveguide for TM mode case also. Then we look at the orthogonality condition. As a consequence, we found that eigenvalues of the modes are real and the modes are orthogonal. Every mode to every other mode is an orthogonal. We tried to understand in terms of the overlap of the modes the two modes we under consideration, that the product of the wave functions integrated over the whole space will be equal to 0, which is the orthogonality condition. Then the another important aspect, that the radiation mode, just to ensure that for guided modes beta should be between n 1 and n 2, the an effective value beta square beta by k naught should be within n 1 and n 2, and we find a set of continuous modes, continuum fields distribution representing the radiation modes. Thank you.